All right, in this video we will be talking about current electricity, which I think is a more interesting type of electricity because we have so many electronic devices around us, and it's good to start on saying the fundamentals of how it works. Obviously, there's probably many levels of complexity beyond what we'll be talking in this class. We're not really going to get into transistors and things like that and that make up modern circuits to do computing and whatnot. But the fundamentals are there, and maybe someday you'll go on and want to learn more about that. So we want to look at, in terms of what we've been experiencing with circuits so far, think about, is there an effect to adding more bulbs to a circuit? Does battery direction matter? Is there just one way to build a circuit with a given set of components? And so these are things that have you do in class, and maybe you already did, and before you watch the video, and just kind of play around with it and see, does it matter if you switch the batteries around? Does it matter if you add more light bulbs? Does it matter how you put the light bulbs in, whether or not it matters or not? So those are all things that we want to understand. Okay? So in order to produce electric current, it's a little bit different than just producing a static like shock, where when we're shocking, like with the Van de Graaff generator or whatever, what happens is that you build up a big potential difference between two objects, and then when you touch and you get that shock, there's just a sudden discharge, and the potential difference completely goes away, and then the current is gone. Well, what's different with electric current is you have something that's supplying a continuous potential difference, so something that's constantly pushing on the charges so that they're continuously moving. We can do that two different ways. We can do that with batteries, which in chemistry you learn how batteries make a potential difference by looking at the dissimilarities in the metals and how they react. And so one really wants electrons, one side of the battery really wants to give off electrons, and so that energy is the driving force there. And then generators, we'll learn a little bit more about the inner workings of a generator when we talk about magnets. But basically you're taking mechanical work and turning it into a potential difference. We can model a circuit like water flowing through a series of pipes. So we don't normally do this with pipes, but it does happen. But I mean, if you think about the pipes in your house, this doesn't happen. But there are reasons for cooling things or whatnot where you would have water flowing in a circle. And so a pump constantly makes it, one side of the pump is at a high pressure and one side of the pump is at a low pressure. And so the water flows away from the high pressure, goes through some sort of restriction, which is like an electrical resistor, and makes it back to the pump. Well, the battery or the generator is like a pump. It makes one side of the battery with a high electric potential and one side with a low electric potential, and the charges flow from high potential to low potential. Now, it should be noted at this point that when we talk about current flow in a battery, as physicists, we talk about positive charges flowing in the circuit from the positive side of the battery to the negative side of the battery, and that is conventional current flow. And this direction of conventional current flow is basically just based on the direction a compass would rotate when put next to the wires, and we can take a look at that. But we know now that it's not positive charges flowing, or not what we call positive charges flowing from the positive to the negative side of the battery. It is negative charges flowing from the negative side of the battery to the positive side. So the actual current flow is opposite what we write. And there are some devices you can use, like if you use a neon bulb, you can tell which way the current's actually flowing. Most components, it really doesn't matter if it's a positive charge flowing one way or a negative charge flowing the other way. You can, in some ways think about, well, holes, like there's a positive hole flowing, but we're not going to get into that. Okay, so it's not that physicists are dumb and don't know about electrons, and that's what really moves in a conductor. It's just that convention's been around longer than when we knew what electrons were. I think all the way back to really long time. Okay, so basically, and I guess I need to move up my animation here because it's being cut out. Uh-oh. It's not letting me grab it. Oh, whatever. We'll just get it. Okay, so for current to flow, you have to have a continuous closed path from one side of the battery to the other. So right now the circuit is considered open and nothing flows. If I click on the circuit closes and now the current can flow from, with my cheesy animation here, from the positive side of the battery back to the negative side of the battery. So remember, closed means on, open means off. Okay, the purpose of electric circuits is to transfer energy. We want to take the energy out of the battery or away from the generator and put it into something that we're trying to power. So the rate of energy transfer has to do with, can be given to us by this following formula: power equals voltage times current. Okay, so that's a really useful thing to know. So basically, if you remember, voltage is joules per coulomb. Our new unit of current is in amps, and an ampere is how many coulombs per second. So if you take a joules per coulomb and you multiply it by a coulomb per second, the coulombs cancel out and you get joules per second, which is the same thing as a watt. Okay, so if I want to know what is the current in a light bulb in my home, so generally, like, light bulbs in my home might be like 60 watts. The voltage in my home is about 120 volts. And so if I want to know what's the current in my light bulb, I would solve for I, which is current. And so I would get the current would equal 0.5 amps. Okay, so that's an example of how we could use that equation. The other really important equation, which is actually important, which I don't know why I didn't put this one first, is Ohm's Law. What Ohm's Law says is that resistance, the amount of resistance you have in a bulb is equal to the, or into any device, sorry, is equal to the voltage across that device divided by the current going through it. Okay, so this V, again, is the potential across. And this I is the current through. And so resistance is just a measure of how hard is it for the current to move through that device. So I want to know what is the resistance of the light bulb in my home. Well, the voltage is still 120 volts. We talked about the current, and just the last slide was 0.5 amps. And so if I take 120 volts divided by 0.5 amps, that means that that light bulb has to have a 240 ohm resistance. When we're talking about circuits, when like in our lab books or whatever, we don't want to always draw out all the different parts, because that would take a really long time. So electricians and electrical engineers, they just use symbols for diagramming circuits, and to make them look nice and neat. Even if the wires go in all sorts of crazy lines, they usually all the lines on an electric circuit diagram, they'll be in nice straight lines. Usually try to use 90-degree corners and everything, so it's easier to follow, like, where's everything going. So some common symbols is, this symbol means a battery, and this is the positive side of the battery, and the other one's the negative side, so positive, negative. Okay. This would be a motor. I actually can't remember what, if this is like a bulb or something. And this is a switch. Other common ones would be like this is a diode. If you have a diode with this little crazy arrow coming off of it, then it's a light emitting diode. So there's some other ones. I don't know why it's not here, but just a generic resistor is kind of a squiggly line. Sometimes it have like how many ohms or whatever it is written next to it. So that's just some different symbols. When we're diagramming symbols, there's different ways for a circuit to be put together. You can put a circuit together in series. So we're just going to use circles for bulbs. So this would be two bulbs in series. Or you could put a circuit together in parallel. Now, each one of them has some different features. Okay? In a series circuit, it's the same current that goes all the way through all the circuit. So let's say, for example, if there's 1 amp of current going through the battery, there's 1 amp of current going through this bulb, and there's 1 amp of current going through that bulb. Okay? So the current is the same all throughout the circuit. Now, when you have a series circuit, though, the voltage drop, if this is a, let's say a 9-volt battery, and if these two resistors are the same, then this resistor here will only have 4.5 volts drop across it, and this resistor will have 4.5 volts drop across it. If I compare that to the series or to the parallel circuit, if this is a 9-volt battery, okay, here the current splits. And so there's twice as much current going through the battery as there is through each bulb. So for example, if there is 1 amp going through this bulb and 1 amp going through this bulb, then there are 2 amps going through the battery. But the voltage drop is the same. If that's a 9-volt battery, there's 9 volts across each bulb, okay, for that type of circuit. So they have different, uses for each kind of circuit. In the series circuit, because all the current goes through both of them, one thing can control another or can respond to what another is doing. In a parallel circuit, those two things operate independently of each other, those two different bulbs. We can control current in a couple different ways. We can use different voltages to begin with, like different batteries. So we use a battery with a higher potential, you'll get higher current. We can also control it with a potentiometer, and we'll show you some examples of potentiometers. So anytime we have like a dimmer switch, that's basically a potentiometer. And basically it's a coil of wire. So what you do is you just have this big resistor, and that has your total line voltage across it. And then you have this little thing that's connected to your device so your device here, like your light bulb or whatever, is in between this, and this little piece can move back and forth. And if it's all the way here, then you have the same potential as the battery or the generator. And if you go down the other way, then you have a much lower potential. Okay. One of the things we'll be looking at is you can use circuits to heat things. We'll be doing that as a way to measure how much energy comes off. So we'll be like putting light bulbs in some water and see how much they can raise the water temperature by. And so we can work some of these example problems later. But just the formula we need to know is just to remember that energy will be power times time. So you could rewrite if you want that energy is voltage times current times time. Okay. When we are transmitting power, so just kind of bring this into terms that you might deal with on your day-to-day life. When you get your electricity bill, you get it in terms of how many kilowatt hours you use. So this is kind of a wonky unit where physicists aren't going to use it because you're combining a couple weird things. Like we tend to want to use energy in terms of joules. So to put kilowatt hours into joules, you would take, so I've got my kilowatt times my hour, okay? And a kilowatt is the same thing as basically there are 1,000 joules per second per kilowatt. So that takes care of kilowatts. And then I'm going to multiply by an hour is the same thing as there are 3,600 seconds per hour. Okay? So 1 kilowatt hour is a lot of joules because here the hour cancels out hour, this seconds cancel out seconds, kilowatt, so we're going to be left with joules. So it's 3.6 million joules is a kilowatt hour. So a kilowatt hour is a huge amount of energy compared to like other terms you've been looking at. Okay, so again, we'll look at in terms of how we figure out costs for different things also in class. Well, that's all the new stuff we have to introduce electricity, which is perfect because I've just about used up my 15 minutes. So hope you've enjoyed the video.